Welcome to the second lesson of E&M. Just two things from the first lesson that I forgot to mention, or three things. One, compasses always point in the direction, or any magnet will always point in the direction that the magnetic field lines point. So if you put a compass right here, it would point up like that. If you had a compass right here, it would point out to the left. Part two, if you were to sprinkle iron filings around here, they'd be ferromagnetic materials in a magnetic field, so they become little magnets while they're in that field because their domains would line up. They would kind of show you the magnetic field lines. They would line up along these directions because they're little magnets and they'd all line up and connect. And then the third thing I wanted to mention is that the denser the magnetic field lines are, the stronger the magnetic field. So just like electrostatics, if you had more field lines or they were denser in an area, there were more of them per area, that would indicate a stronger field. Same thing with magnetic field lines. All right, on to the new material. We'll talk about solenoids, which is a fancy word for coil. But before we get to that, we have to talk about notation. So we got to represent a bunch of this stuff in 3D due to the fact that the formulas for electromagnetism use effectively what's called a cross product, which we'll learn about in university. Anyway, so it's inherently three-dimensional. So we're going to have to represent current flows in 3D due to the way it works, which is a little difficult on a page, but to do that, we have these two symbols, which will represent either currents or magnetic fields, and hopefully that'll be clear in the circumstance. So this is supposed to be a little black circle, or a little black dot. I didn't quite pull off the circle, but you get the idea. And that implies that something is coming out of the page at you. It's coming straight out. A cross implies that something is going into the page. That you got a field line or a current going into the page. Now, the way you remember it is it's supposed to look like an arrow, like a bow and arrow archery. If you have an arrow pointing out at you, you just see the point, right? So you get the circle. So something coming out at you. If you've got an arrow going away from you, you just see the feathers. Just see the feathers there. Those are supposed to look like the feathers of an arrow. Anyway, so into the page, out of the page, into the page, out of the page. Remember that, and it will be used to determine direction of conventional current, because we'll be using conventional current, because people have been using it for a long time and came up with all these rules based on it, though you can reformulate them with electron flow. But we will use conventional current because then people won't think you're crazy when you talk to them later, because everyone uses conventional current. Direction of magnetic field. Okay, let's talk about the first right-hand rule. Now there's going to be 3 right-hand rules, I believe I'm going to teach you. And the most common mistake, which I've even helped people with in university, is using your left hand when you're supposed to use your right hand. Now this is more common than you think because most people are right-handed and they'll be writing a test and then their left hand is free. So they'll start trying to do it with the left hand, but then of course it doesn't work. So do make sure you are using your right hand for the right hand rules. An interesting thing, if you have current flowing in a wire, it will create a magnetic field in a circle around it. Strongest, closest to it, and getting weaker as it moves further away, shockingly. The way you determine the direction of the magnetic field, the direction a compass would point anywhere around a wire containing current, is use the right-hand rule. So, this is supposed to be the wire part coming out of the screen at you. And these are the magnetic field lines around it. The red is the magnetic field, black is the current carrying wire coming straight out of the screen at you. So if you want to determine the direction of this magnetic field, you get your hand like this. Your fingers naturally curl in the direction if you're using your right hand. Thumb points in the direction of conventional current, so out of the screen. And then your fingers will point in the direction of the magnetic field around the wire. So yeah. That is your first right-hand rule. You've got one current carrying wire and you want to know the magnetic field around it. Think this through until it makes sense. Try it out. Notice it would be going the other way if current was going into the page. Right now, for this, current is coming out of the page or out of the screen, so thumb pointing in that direction. Thumb, direction of current, fingers, magnetic field lines. I remember it thinking kind of like, hey, you got a lot of magnetic field lines, only one current. You got a lot of fingers, only one thumb. So field lines, fingers, thumb, conventional current, though that will switch for the next one to make things perfectly clear. All right, that's the first right-hand rule. Let's talk solenoids and the second right-hand rule. So a solenoid, if you ever want to sound fancy, use the word solenoid, but it's just a fancy word for a coil of wire. Coil of wire is a very effective electromagnet because you get this whole effect going on, but if you think about it, the magnetic field inside the coil, it's all adding up, and outside really. So if you just do the first right-hand rule, starting from here, and move your hand, thumb pointing in the direction of the wire, you'll notice that at all points, the magnetic field inside the coil is pointing towards north and away from south. So these field lines that you saw right up here, a solenoid has exactly the same magnetic field as a bar magnet, except it's got field lines going from south to north inside it. So these become full circles, or ellipses, or whatever the heck they are. All right, and another interesting point, the magnetic field, as long as you're not right near the edge, is identical everywhere inside the solenoid, whether you're right beside the wires or you're straight in the middle or whatever, and that's because there's a certain amount of symmetry. The strength decreases with distance, but kind of like if you're closer to some wires, they're providing a lot of magnetic field there, but you're further from most of the rest of the wires. So their effect is diminished, but the net effect is canceled. Anyway, I won't go through the math, but just the net effects of getting closer to wires, so their little contribution is bigger, and then being further away from all the rest of the wires, it ends up canceling out. So it doesn't matter where you are inside this coil, your magnetic field is identical everywhere in there. Your second right-hand rule to figure out the direction of the magnetic field inside your solenoid, you notice how you got a lot of loops here? So we're going to take our fingers and we will curl them in the direction of conventional current flow. In this case, it's looping around and around and around and around. So the conventional current is always kind of going like that through all the wires. Your thumb will be the direction of the field lines. So in this case, they're pointing towards north, shockingly, because it always will. But if you don't know north, just do the second right-hand rule where your fingers are conventional current now, because you got so many coils, and your thumb will be the direction of the magnetic field. And this is the right-hand rule just for solenoids. You can also use the first right-hand rule to figure it out, but it's convenient to have the second one. We can also calculate the magnetic field inside the coils if we know how many loops there are and the length of the coil, or just the loop density, because that's what matters for determining the magnetic field. It depends on current, how much current you're shoving through that coil, and the loop density, how many loops you got per meter. So let's talk. We haven't measured magnetic field strength before. Let's take a look. Magnetic field strength has the symbol B, obviously. Magnetic field strength. Why wouldn't it be B? Not obviously. And it's measured in something called Teslas, or T. Teslas or T for magnetic field strength. It's got this new constant, which has a totally sweet name of the permeability of free space. It's one of my favorite named constants, and this is always 4 pi times 10 to the minus 7 Tesla meters per amp. Yeah, 4 pi times 10 to the minus 7. It's just like the universal gravitation constant or Coulomb's constant, the 9 to the 9. It's always the same, and just a number to make our units work. We picked currents in amps and distance of meters. They're not magical, and so we need these constants to make everything work out. All right, so yeah, our formula is our magnetic field strength equals this constant, permeability of free space, times the current in amps, times the number of loops, all divided by the length of the coil in meters. We can also abbreviate this. You sometimes see it like this. It's the exact same formula, except instead of saying loops divided by meters, we have a loops per meter variable. So if you're given loops per meter, use this guy, which is the same thing as loops divided by meters. And if you have loops and length of the coil, use this version. Same idea. And then we will practice it. So next step, open up your snap book and turn to the first section in there. I will also include a PDF of it in case you left it at the school. Thanks for listening.